My name is Haley Hollinshead. I'm a UAS student, and this is my final Spectra analysis video for Organic Lab Semester 1. And this is for Professor Szabo. So the first thing we look at is the mass spectrometry. And right away, the first thing I want to do for my compound is calculate the degree of unsaturation. So as we can see down here, I have the formula written down for the degree of unsaturation, and that's going to be 2 times the number of carbons plus 2 plus the number of nitrogens minus the halides minus the hydrogen number, all divided by 2. So when we plug all of our numbers in based on our formula, which is up here, C10H12O, we get a degree of unsaturation of 5, which means that we could have a combination of possibly 3 triple bonds, a ring, or, 3 double bonds, a ring, things like that, just to make sure it adds up to 5. So the next thing we look at is right here. We have 148 for our M+, and that means that that's what the mass of our compound is. So that's our M+ right there. And then we also see that our base peak, which is the strongest peak on the spectra, which also signifies the most common fragment, is 105. So the difference between our M+ and base peak actually gives us our fragmentation pattern. So I'm going to take 148 minus 105, and that gives me a fragmentation pattern of 43. And then just based on my molecular formula, I can tell that there's no bromine, iodine, or chlorine in the molecule. This is the kind of layout that we're going to be following for our infrared spectroscopy. And by using this, we can kind of see where different bonds stretch and determine what kind of functional groups we might have in our molecule. So this is the infrared spectroscopy analysis, and as we go I'm going to be uncovering our 5 different zones to kind of see what we have within them. So in our first zone we're going to be looking for things like primary amines, which kind of look like vampire fangs, alcohols, 2-amine or terminal alkenes that kind of look like V's, or carboxylic acids, which kind of look like beards. So if we uncover this zone, we see that we don't really have anything going on here. We do have some slight peaking up here, but that's probably not enough to clarify that this is an aromatic. So we'll just go ahead and wait for the rest of the analysis to determine that. This is our second zone right here. And in our second zone, we're actually going to be looking for C to H, sp3 bond stretches, aldehydes, and carboxylic acids as well. So if we remove that, we can actually see that we have these peaks coming in front of 3000. Right there we can see it's at 2962 and 2874. So this is signifying that we do have C to H sp3 bond stretches. And this little marker right here, that is a good indicator that we probably have an aromatic. If we move on to our third region, which is right here, we're actually looking for triple bonds in this region. So we're looking for carbons triple bonded to other carbons, or carbons triple bonded to nitrogens. This region could also be an indicator of an aromatic as well. But as we can see, we don't really have anything going on there, and we can pretty much say that there's nothing in this region. For the fourth region, right here in yellow, we are looking for carbonyls. So that's a C double bonded to an O. It can be any carbonyl group. And this strong peak right here is a sure signifier that we do have a carbonyl. So in our last section, right here, number 5, we are going to be looking for alkenes and signifiers that we might have a benzene. So as we can see, we do have a lot of strong spikes coming through this region. So we can probably assume that we're going to have a benzene ring in this structure. So like that. Once we go on to carbon and proton NMR, we're going to be able to determine the structure a little bit better. But from this, we can pretty much assume that we're going to have a carbonyl and a benzene ring. So here we have a guide to proton NMR chemical shift values, and this can be kind of helpful when we are doing proton NMR to try to determine where the shifting is occurring and what could be causing the shift. The next thing we are going to look at in our spectra analysis is proton NMR. And the first thing we're going to do is look at our integration numbers. So these are the numbers directly over each of the peaks, which I've highlighted in gray. And this signifies how many hydrogens we have in a specific environment, like how it's being downshifted by electronegative atoms, or kind of like where it's sitting in the molecule. And our integration numbers actually add up to our total number of hydrogens in the molecule. So as we can see, we have 2, 1, 2, that's 5, 2, 7, 2, 9, and then plus 3 is 12. So we know we have 12 protons accounted for in our proton NMR. The next thing we look at will be our N+1 neighbors right here. And you can find this by looking at whether the peaks are singlets, triplets, doublets, quartets, things of that nature. So you can't actually see it in this drawing specifically because the other one was too large to fit onto this page, but each of these peaks, it may or may not have a couple more peaks involved with it. But when I was doing my background work for this, I actually looked at how many peaks each one have. So, and looking at that, we find our number of neighbors, because we take our number of peaks we see, we do N+1, and N is the number of neighbors. So here we're going to have 2 neighbors on this CH3 group. We're going to have 5 neighbors here. We're going to have 2 neighbors here, 2 neighbors here again, and then 1 neighbor over here. And according to these numbers, we can tell then that this peak over here was a triplet, this peak over here had 6, this peak was a triplet, 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 and then doublet. And then on top of all of this, we can actually determine, based on how downfield shifted these hydrogens appear, how close they're probably going to be to the electronegative atom that we have in our molecule, which in this case is going to be oxygen. So we know that these protons over here are going to be the closest to the oxygen, because they're the most downfield shifted. We can also see that these down here are probably going to be the farthest away, right here. So according to our proton NMR, our mass spectrometry and infrared spectroscopy, I have drawn this structure. So as we can see, this structure fits the requirements that we needed according to our different analyses. So we can see right here we have 3 hydrogens with 2 neighbors, and that is satisfied in our drawing right here. As we can see, we have these 3 hydrogens, and they are surrounded by these 2 hydrogens right here. We then have 2 hydrogens that are surrounded by 5 hydrogens. So we can see these 2 hydrogens right here that are then surrounded by these 5 hydrogens over here. Yet again, we have 2 hydrogens right here that are surrounded by 2 other hydrogens, which can be accounted for right here, these 2 hydrogens that are surrounded by these 2 hydrogens. And then once we move over to our benzene ring, we have 5 hydrogens here, which can be accounted for in this section where we have 5 hydrogens. So we have 1 hydrogen surrounded by 2 hydrogens, 2 hydrogens surrounded by 2 hydrogens, and 2 hydrogens surrounded by 1 hydrogen. And these can all be found in our benzene ring. In addition, we also see that we have our carbonyl group that we initially predicted in our IR analysis, and we also have the benzene ring that we also predicted in our IR analysis, as well as our C to H sp3 hybridized bond stretches, which can be found over here. In addition, the proton NMR chart that showed where things shift to actually showed that we probably were going to have a ketone, which is what we ended up having. And we knew this because we saw that a ketone would probably show up around this 2 range in our proton NMR spectra. Finally, we also see that our degree of unsaturation is met because we have 1 ring, 3 double bonds here, and then 1 double bond here, which gives us a total degree of unsaturation of 5. And finally, we have our carbon-13 NMR. And this guide can show us kind of where the shifts are in our spectra that can help us kind of determine what carbon environment is which. And this brings us to our last section of analysis, which is carbon-13 NMR. And from the get-go, we can see here that we're going to have 8 different carbon environments signified by the 8 different peaks in our spectra. Now, as we could see on our carbon-13 NMR shift table, the most downfield shifted, which is right here, is going to be our ketone. So that's going to be our carbon double bond into O, located right here in our molecule. In addition, we see that these carbons in this region are falling within the aromatic range of the downfield shift on the C13 NMR. So these are going to be our aromatic carbons. In addition, due to how far away this last carbon is right here from the oxygen, I'm pretty much assuming that this is that peak right here. It's been shifted a little bit because it's a little bit farther away, because this only accounts for 4 of our carbons in our aromatic. And then finally, our last 3 carbons are accounted for in this section right here. And these carbons are actually right here in our molecule because they're just our regular sp3 hybridized carbons. And that brings me to a conclusion for this analysis. Thank you again for watching, and thank you Professor Szabo for a fantastic first semester of Organic Chemistry Lab. Thank you for your time today.